Dr. Paul Hernandez-Herrera holds a PhD in computer science with a specialization in machine learning and image processing. He is currently a CZI imaging scientist at the Mexican National Laboratory for Advanced Microscopy. His research focuses on developing computational algorithms to automate image analysis, including applications such as cell, sperm, root segmentation, and cell tracking. In recent years, he has been focused on the applications of deep learning to microscopy images. So thank you so much for being here today, Paul. I'm going to stop sharing my screen and let you take over. Thank you.
Hello, Vanessa. Thank you very much for the introduction. So I am going to share my screen. Let me see. Okay, I think that you can see my screen.
Yes, looks great. Thanks.
Okay. Hello, everyone. Today, I am going to give a talk about deep learning for biomedical image analysis. As you see, this topic is deep learning is computer science, but it is applied to biomedical imaging. So it's medical images or biological images. So we are going to have, we have two different type of knowledge, computer science, biological or medical. So we are going to see how these work together. And it is really interesting. I really like this kind of stuff. First, I would like to talk about where I am working. I am working on the Mexican National Laboratory for Advanced Microscopy. It was funded in 2013 here in Cuernavaca, Mexico. You can see, can you see my pointer? Vanessa?
Yes, yes, we can.
Okay, so here is Cuernavaca. It was funded in 2013. Then a second core was funded in 2015, 2 years later, here in Mexico City. And in 3 years later, the third core was inaugurated in Baja California, Mexico, near to USA. So we have here the third. Here, they have expertise. They have a lot of knowledge on confocal imaging. TIRF, FLIN, bioluminescence, super resolution, in vivo imaging, cytometry, spectroscopy, and electronic microscopy. And they have even more expertise on different acquisition modalities. But these are the main acquisitions that they work. As you can see, my expertise is not in this area. I know a little bit about this, how you acquire the images, how do you prepare the samples. This is not my expertise. My expertise is in mathematics. I did a bachelor's in mathematics. I spent probably 7 years taking courses about calculus, algebra, mathematics, logic, differential equations, linear algebra, a lot of mathematics. I have my background. Then I decided to do a PhD in computer science. I changed from mathematics to computer science. I took courses on digital image processing, machine learning, computer vision, pattern recognition, data mining, and many other courses related to image analysis. As you can see, my background is computer science. I am working on a core facility that they have expertise on different imaging modalities. I know that at least for me, I cannot cover everything. My expertise is computer science. I cannot cover the biological part. I don't know anything about acquisition. I know that many people from the biological part, they are very good at the biology, and they cannot do computer science. I know there are some genius that they can make mathematics, physics, computer science, and biology. I know some genius. But for me, it's only mathematics, computer science, and I cannot go to the other side. But when you join two people together from the computer science and from the biology, it's really interesting because you can do a lot of interesting things in research. So for me, I have more than 15 years of experience on image analysis. As I say, I did my PhD around 2009. And I started working with biological images. Actually, my first project was segmenting neurons, trying to extract the center line, trying to detect the branching points for images, for 3D images. And in this paper, I will showcase some of the applications that I have been working on microscopy images and some of the algorithms that I have developed and some of the tools that I have been working for the bioimaging community. So as you can see, as I say at the beginning, I don't know, I am not expert on acquiring image. So I only receive the images. For example, this is Arabidopsis root. I know that it was acquired with a confocal microscopy. I don't know how was prepared the sample. I don't know what are the parameters. This is not my expertise, but I know that I have images. Some biologists come to me and say, okay, we need to track how the nuclei are dividing. And I want to see how much time it takes to divide. For example, in this example, you see how the root is dividing, and they say, how can we do it automatically? How can we solve this problem? For example, here again we have neurons. This was my first project, and we were interested in detecting the branching points. How many branching points can you obtain? How many branching points you have in this neuron? So this was a really interesting problem. And as I say, you can have a variety of images. You can have nuclei, neurons, root. Here we have another example that you have Arabidopsis root. We have trichomes. We have a sperm. We are also working with bright field microscopy. You have the sperm that is swimming, and you need to extract information. So for the images, it is really important to acquire images because images allow to observe biological structures at the micro or nano scales. But with the images, you can observe, but it is also really important to extract measures, to extract information, to extract numbers from this image. And I am working on this part of the science where I try to extract information, extract numbers, extract sizes, extract branching points, extract velocity. So I am working on this part. For example, if you are working with nuclei, so you want to see the cellular proliferation, see if you count the total number of nuclei. For a sperm fluorescence intensity, it gives you information about the specific markers, trichomes, the distribution. It helps identify patterns of locations, time of cell cycle. So it is really important for understand the growth dynamics and development process for neuron. So this was my first project, neuron. It was really interesting to count the number of branching points. So this indicates the complexity and connectivity of neural networks. So you work on this part, and it is really important to extract these numbers, these measures, and how you make it is really important. I know people that spend probably few time acquiring images, so probably they know the biological part, how you can get the images. It can take probably 1 month, but it can take 3-4 months to just extract the information, the important information about this data. So it's really important to make this more efficient, this analysis, and this is what I work. So when you want to extract information, probably many of you are familiarized with Fiji. Fiji is a really good tool. It allows to extract information. For example, here we have nuclei, and you want to count or you want to extract the size of each nuclei. So what you do is what I have observed, not you, but what I have observed is that you go to the image, you label each nuclei, and it can take probably 1 hour to label one image. It can take 2 hours. It depends on the complexity. So once that you have labeled, you can extract the information, and that's enough. Here I show 4 examples where you label these nuclei. It is really important when you do this process that you make it efficiently. So manual annotation sometimes is really tedious. So it is impractical when you have many images. You can have, for example, if you have 2, 3, 4, probably 10, 20 images, you can say, okay, I can do it manually. It's going to give me very good results. It's the best. It's the best to do manually. But if you are working with 200 images, 1,000 images, If you want to analyze 10,000 images, are you going to do it the same way? So, as I say, I have done it manually. I had spent months manually labeling data, and it is really impractical to do that. I am going to show one example that I spent probably 1 year labeling data, and as I say, we could work analyzing data instead of manually annotating data. So another thing about manual labeling is when you repeat the process, there are several papers that say, okay, if you do manual annotation one time and you do it probably 1 week later, two months later, it is not going to be exactly the same. You are going to have difference. So this is something that is really important. Reproducibility is not as good as when you work with different tools. Oh, okay. So what would be really useful? So let's assume that you have a task, for example, the nuclei labeling, and you want to label each nuclei. So you are working on labeling the data labeling. It could be very useful to have a method that learns to reproduce these tasks. When I say reproduce, I mean that you give the images, you say, okay, this is my image, I want to obtain this. And for some reason, for some magic, this black box say, okay, you have a new image, I am going to do exactly the same as you did on the previous image. That would be really helpful. And this is something that I have worked probably more than 15 years. I have been working for more than 15 years, and it is a really difficult task to do that. So there are several tools, several algorithms that allows you to do that, but it is difficult. At least 7, 8 years ago, for me, it was really difficult to work on this, to repeat this manual processing. And what we use is artificial intelligence. We have it now. It is called artificial intelligence. We have this magic tool that if you say, okay, I have this image, I want to obtain this, I can obtain this black box that if I gave a new image, it is going to obtain something very similar as if you were doing the manual labeling. So I am going to explain briefly how this works, and I hope that at least you have a general overview of this method. I am not going to go deep on this methodology, but I am going to try to explain something really fast. So if you are working with biomedical imaging, or you work with nuclei segmentation, and you know STAR-this, or you have used STAR-this, cell pose, then you are using artificial intelligence. All these methods, cell pose, and STAR-this, use artificial intelligence. We have another tool, Morphograph. Also, Morphograph is using artificial intelligence. QPAD is also using artificial intelligence to help analyze better the images. Napari, there are several plugins using artificial intelligence. Elastic allows you to do supervised machine learning. It is also using. And there is this tool that I really like a lot because this is the state-of-the-art methodology, zero-cost deep learning for microscopy. It allows you to easily train deep learning algorithms for segmentation, denoising, super resolution, object detection, and image-to-image translation. So there are several tools over there. Probably I am missing a lot of these tools. Probably you know more tools if you work on a specific project, but there are several tools based on artificial intelligence. BAA 3D, this was I worked on some software to include my algorithm over there. BAA 3D is for neurotracing. It has probably more than 20 different neurotracing algorithms, and it allows to extract the center line from neurons really fast. You can use one algorithm, another algorithm, and you have several options to trace the neurons. So we have on Fiji also, we have Deep Image J. This is a really nice tool. So you only need to put your image, you download one model that is already trained in some images, and it's going to give you some results. It has for several different tasks to automatize different tasks. And it is not only on biomedical imaging. It has many applications. If you know, probably you know ChatGPT. So a lot of people are talking about ChatGPT. It helps many things to check grammar, to many things for helping people. So ChatGPT is also based on artificial intelligence. So virtual assistants, Alexa, Siri, Cortana, also you can say to run the light, and it's going to run the light. So it needs to read, it needs to understand that you give an instruction, it needs to convert the voice to letters, the letters it needs to interpret these letters. So these are also working on with artificial intelligence. So self-driving cars, you know that there are some places where you can drive cars. So this is really nice. You don't need to drive, so it drives autonomously. Marketing. So you have many applications of artificial intelligence. But what is artificial intelligence? So there are several definitions. So it just, you can say, is the simulation of human intelligence in machines, enabling them to learn, reason, and perform tasks autonomously. So it tries to reproduce the human intelligence. So there are several examples. For example, for playing games, there are machine learning or algorithms that are able to beat the best human players. So they are very good at playing games. For example, I say virtual assistants, robotics, and medical imaging. So there are some machines that are able to detect cancer. They are even able to detect cancer with more. They are better to detect cancer better than medical experts. So there are some cases that the machine is able to detect cancers that the human is not able to detect. So these are some applications. But as I always say, you have to use the artificial intelligence intelligently. So you are not going to trust everything. So you just have to give the image. The machine is going to give you some clue. They are going, okay, here is cancer, and then I think that it needs to come and a specialist and say, okay, yes, you are true. It is just a suggestion right now. You need to use this as a suggestion about the problem that you want to solve. It is not only on this, as I say, it has many applications on biomedical imaging. In here, we can see an example where you have nuclei, you have cells, and you want to detect the nuclei, you want to detect the cells. About this artificial intelligence, there are several branches from artificial intelligence. Some artificial intelligence work with vision. For example, self-driving cars use a lot of vision. So there is one branch that is only dedicated to this. Speech, for example, Alexa, all these virtual assistants, they need to understand what people say, processing, natural language processing, expert systems. So this expert system is, for example, medical, that you want to take a decision. They allow you to work on this. Robotics. And I am working on a specific branch. I am working in machine learning. And what is machine learning? Is the science of making a computer learn and not like a human, and improve his learning autonomously through data. I think that this is the most important part. It is learning through data and information in the form of observations. We need to give examples to the machine to understand what we want to reproduce. So, for example, in the case of nuclei, I have my image, my input image. I manually annotated this image, and now that I have this input image and what I want to give, these are my observations. I say to the machine, okay, just try to reproduce this task. And this is what is the most important part. If we don't have this information, if we don't have what we want to obtain, what is my input and what I want for output, it is going to be very difficult for the machine to work. So for me, this is the most important part. Information in the form of observations. The good thing is that we have something that is called deep learning. Deep learning is something that allows to solve problems. As I say, we wanted something that I have my input, I have my output, I want to some way to transform my input to my output. And we have this tool that is called deep learning that it allows to solve this problem very, very well. So now nobody's working with, well, people are working with some other methodologies, but deep learning is the best that you can use. It allows you to solve really, really well this problem. And how this deep learning do this task, you are going to have, for example, let's assume that you have an image and you want to say, okay, is this a bird, is a sunset, is a dog, is a cat. So we want this to classify. This is a classification problem. You want to give to this image, you want to give a label. So in this case, it's bird. So deep learning is just transform the data, apply filters, and they apply something that is called neural networks. And at some point, it is going to give you a probability. It is going to be the probability to be a bird, a sunset, a dog, a cat. So you expect that the probability it is very close to the label of the class that you want. In this case, you expect high probability, for example, close to 1 to this class, to bird, and probably very low probability to this, to sunset, dog, cat. Probably you are going to have, you expect to have this low probability. We don't really care for most of the problems. You don't really care what is happening in this part. You don't care about the transformations. You don't care about what is doing deep learning. The only thing that you really care is that it is good output. So this is the most important part. I don't care about this. For this part, I only care that the output is what I want to do. And as I said, this deep learning is very good at doing that. So you have also another problem. Segmentation. Segmentation is not giving a class. I'm not going to say, okay, I want to give this medical images. I want to delineate regions. In this example, I delineate or annotate 2 regions. When I receive this image, I want to transfer this image to these 2 regions. So, and again, you have a different architecture. It is going to apply just transformations to the data. It has a lot of parameters. There are some networks that have more than 30 million of parameters. 100 million of parameters is a really, really, really complex network. You don't know what is happening inside this network, but you only care about that the input is sent to the output. If this happens, so you are going to be, you are able to solve the problem. And this is really important because you don't really care what is happening here. You want to obtain the output. You want to automatize your process. You don't want to repeat the manual labeling always. You want to find something that repeats the task for you. And deep learning is doing exactly that. So here I am going to briefly explain how deep learning works. So let's assume that you have an input. So you have an image and you want to obtain the manual annotation. You have these 3 nuclei. This is the shape, and you have your network architecture. It can be probably 1 million parameters. You don't really care about right now, you don't care about the parameters. So you just need to focus that these parameters are fixed. So once that you have your model, it has values for the parameters, for the 1 million parameters. It can be a value 1, 0.1, negative values, positive values, so large values. So you don't really care about these parameters, but there are a lot of parameters that you have in this network. Once that you have fixed these parameters, you are going to have your model. So you are going to apply this model. Okay, you are going to have your input, you have your network. With these parameters, you are going to apply all the transformation to this image, and the model is going to give some output. As you see, the model say, okay, for this image, my output is this one. So as you see, the expected output is not something similar. So what is happening? So my model is not working. So we need to train the model. We need to train the model to say, okay, you are having errors. You are having this model is really, really bad. It is not doing what it should do. So you need to somehow compare the model to the output, and based on this information, you need to update your weights. And this is the second step. Once that you have the model output, you compare. You can just compute the difference, the mean square error. There are several other the dice coefficient. There are several ways to compare these two outputs. In this case, you have a lot of errors. If you have a lot of errors, it is going to say, okay, so this model is bad. So you need to update your weights or your parameters drastically because it's doing really bad. So, and this is what it's going to do. It's going to compare. It's going to say, okay, these two images are really, really different. Just update the parameter of the model, and it is going to create. So this is updating, and you are going to have another model. What you expect? You expect with the new parameters, and you apply the input image. This new parameter is going to give a better approximation to the output, and this is what is really happening. This really happens in the deep learning training. This is the reason why I say that it is always really, really important to have a good training set. In this case, training set is the input and the expected output, because this training set, it is going to guide the architecture, and it's going to update the parameters to the expected output. So once that you have this result with these new parameters, again, you are going to compare, and it says, okay, so my model is doing good. I don't need to change these parameters of the model a lot. I only need to change it slightly just to have a better approximation. And you do this, repeat this process with a lot of images, a lot probably. You can use 100 images, 200 images, and this is going to give a model that is able to reproduce what you have in the input and you have in the output. Once that you train the model, you expect to reproduce this task from input to output. So, as I say, this is a lot of maths. Doing this requires programming skill, a lot of programming skills. So it requires also a deep knowledge of mathematics, a deep knowledge of machine learning. 7 years ago was really, really difficult to do this. It was really, really difficult, and it was almost only a few people were able to do that. What I am working on enhancing accessibility of this algorithm for the research community. As I say, this is the state of the art. If you can use it, if you want to solve this laborious task of manual annotating, you can do it. So this is my goal, just to develop several algorithms to make this process of training or generating a model more easy. So I am developing Fiji plugins with user-friendly graphic user interface. Important, I am designing Jupyter notebooks for improved usability. I provide user-friendly Python code release. So some of the tools that I have developed is deep learning for segmentation to the images. Many of these are, I am still working to make it more easily accessible and more easy to use. Right now, many of them are very easy to use. So you can just go GitHub, download the code, and you can run the code very easily. So it's deep learning for segmentation, just when you want to obtain regions for 2D images, for 3D images, classification, when you have an image and you want to give a label, you can say, okay, this image is sick. For this image, the label is sick. It's not sick. It has the DC. It doesn't have the C. This image is high intensity, low intensity. It depends on classification what you want. It depends on the problem that you want to do. And this code is really easy to use. Replaced, I also developed a tool for cell image tracking. I am not going to go deep in this. I am going to go only deep on the deep learning algorithms. For segmenting tubular structures, this was my work on my PhD, sperm center line tracing. And I really like mathematics, so I am working also in a lot of mathematics. I developed these filters for images in filter images in Fourier space. I really like mathematics, so I also work in not only on the computer science but also on mathematics. So as I say, do you remember that I say, okay, we need the input image and the training images to do deep learning, and then we need to optimize the parameters. We need to go from these images. So what I developed is Jupyter notebooks. And the only thing that you need to give is where is your input images, where is your output. If you have those two parameters, you can do deep learning. You can just solve this problem for the task that you are developing. So you don't need to do anything else. You only need the input image, the output image, and that's it. So there are some additional parameters. You can set this, but if you have more knowledge about this deep learning, you can modify these parameters. They are very easy to modify. They are very easy to use, but you don't need to modify. You just use those parameters, and the model and the training is going to work really well. Once that you have the model training, you can apply this model to new images, and it is going to take probably 1 second per image to solve this manual labeling. So I also have the deep learning for segmentation for 3D images. Again, as I say before, you only need two things: the input images and the target images. And you have some additional parameters. But as you see, these parameters are exactly the same as for the 2D case. So we don't have nothing different. It's exactly the same. And we also have the method, the code for classification of 2D images. Here you have to give the path where are the images with class 1, class 2, class 3. You can have many classes. And the good thing, you have exactly the same parameters as before. So this is something good, because if you know how to use the model for segmentation 2D, if you learn how to use the segmentation for 2D, you can use the segmentation for 3D, and you can use the classification for 3D. So the code is exactly the same, and you don't need to modify anything. You can do, if you learn to use one Jupyter notebook, you are able to use the 3 of them. So this is really nice. So as I say, what do we need to use deep learning? So we need the training set. This is the most important part. This training set is what guides the model to reproduce your task. For example, you have this input image. This is trichomes. You need to label where each of the trichomes. If you have nuclei, you need to label each nuclei. If you have the sperm, you need to also label each sperm. Now, the final part and the interesting part. How can you use this? So these are some applications that I have been working for different projects. For the cytometry, if you are familiar with the cytometry, it allows to obtain a large amount of data. So you can obtain probably more than 10,000 images per experiment. So it's a lot of images. And what we observed when I was working with this, when we were working with this project, is that some of these images are not useful for preprocessing. So you need to discard those images because you cannot analyze this image. In this case, we were interested in segmenting the sperm. So only sperm that were on focus, those were really important for us. We needed to detect those sperm. So we select class 1 as sperms that were in focus, and class 2 as those sperms that were not in focus. And we use this code. Instead of number of classes 4, we select 2 classes, and we give the path where we put all these sperm in focus, the folder where the sperm not in focus, and we train the model. We train the model, just click, and we are ready. Once that we train the model, we were able to do this process efficiently. One interesting thing, when you train a model, sometimes it takes a lot of time. For 2D images, it's not a lot of time. I think that for these images was 7 minutes probably to train the model. So it was really fast. So it is not going to take a lot of time. It's just 7 minutes. So 7 minutes, probably you spend 1 or 2 days doing this, separating these 2 classes, and that's all. That's all. You are ready. And once that you are ready, you train the model, 7 minutes, and we obtain a F1 score classification of 0.99. A value of 1 indicates a perfect classification. It means that you don't have errors. A value of 1 indicates the worst case, but 0.99 is really good. These are one example of images automatically selected. This is what the model select. Once that you train the model, I say, okay, now I am going to select another images and just try to separate this. And this is what is separating. This gives us class 1, and these are really images that we can use as post-processing or to analyze these images. And class 2, these are images that are not used for us. The algorithm is saying, okay, you use discard, just don't use it. And that's really good because now we solve the problem. Probably 2 or 3 days to solve this problem. It's really good. So it's really good to invest this time. The second task, once that we have the images that now we were able to pre-process, we wanted to detect the head, and we wanted to detect the flagellum. So the biologist experts say, okay, he drew the head, he drew the flagellum, and he did for 236 images. I don't know how much time, probably 3 days. I don't know. I don't have the time, but it was not a large amount of time. And these are some examples. This is my training set. This is my input image. This is what I want to obtain. This is my input image. This is what I want to obtain. This is my input image. This is what I want to obtain. And we trained the model. It took 40 minutes approximately. And this, we measured the dice coefficient. The average value was 0.89. A value of 1 indicates a perfect classification. It means that you have exactly the same output as the input images. And 0 is the worst case, that you are doing really bad. So, and these are some examples of the input image of the output. This is one example of dice of 0.46. This is my input image. This is ground truth. And you see the model was not able to detect the head. So that's the reason that it gave a really bad value, because it was not able to detect the head. Probably it's because the head is not in focus. I don't know. Something happened, but it is always good to show not only the good results, but also the bad results. So in this case, this was really bad because it was not able to detect the head. But as you see, this is a dice of 0.81. This is the average performance. And it's really good. It is able to detect the head, it is able to detect the flagellum, so it's really good. And we have some very good cases where we have a dice of 0.93, and this is almost exactly the same. So this is really good. What happened here? Probably is because we only have 236 training images. Probably if we increase the number of images, probably if we use 500, probably this is what I am going to say to the biologists. Okay, probably if we increase the size to 500 images, we are going to have more variability on the images, and we are going to have probably a better performance. So we are going to see. This is one of the paths that we are going to take. We are going to try to increase the training set to see if we are able to improve this result. But at least in most of the cases, the model is doing really well, and it took only 40 minutes to train the model. So it's good. It's good. So we also have we also applied this model to the images. We wanted to track the sperm head. So we manually annotated 40,000 images. So you say, how did you annotate 40,000 images? Yes, we did. We annotate this large amount of data because really we needed to extract some information. We annotated these images, and we say, okay, we annotated a lot of images. Why don't we do it automatically? And this is what we worked. So once that we annotated a lot of images, I say we are going to use deep learning, just solve the problem, and just train the model, just use the code, and you are going to be ready to solve the problem. Let's see. I don't have numbers for this, but I have a really nice video. This is the video. So you can see the circle is really detecting the position of the head. And this is automatic. You don't need to do anything. Just train the model and just apply the images. So now we don't have to do any more annotation. We don't need to spend months annotating images. Just apply the model. Probably in 1 hour, you are going to have the work that we used to do it on 2 weeks. So just, as I say, spend the time with the manual annotation. So we also have a sperm in 3D data. So this was even more difficult to do that. It was the annotation in 3D data is difficult. We had probably 30,000 annotations. It took more than, I think that we had spent more than 4 years annotating, 3-4 years annotating. So it's a lot of work that we have done. And again, I say, okay, we have the annotation. Why do we need to still working with annotation? Just let's use deep learning and just try to see the magic. And this is the magic. So for this training, it took 5 days. So as I say, this is a really difficult problem. Okay.
There we go.
As I say, it's really interesting that we are able to solve this problem. So in this case, I show the red line. This shows the manual annotation, and the overlay with the gray line shows the output of the model. So now we are able to solve this problem. And we also have different applications. We have applied this to trichomes. We have this example. We have the input, the manual annotation, the model output. So in most cases, this manual annotation is identical to the automatic. In some cases, the automatic annotation outperforms the human annotator. In other cases, the automatic annotation uses some trichomes. So these are some cases that, in few cases, it is not able to do it really well, but in most cases, it performs really well. So applications to nuclei, we also train this model for nuclei. These are example of the input, manual annotation, and these are example of the output that we obtain. So this allows to solve this problem. One thing that we observe is that, for example, cell pose is already trained on different data sets. So when you use cell pose to classify your data, it works really well. But cell pose studies and explain this, those work really well. But what we observe is this red line. This is the red line is a start this when we train with our data, and the blue line is a start this when we use just the model that they use. So as you see, the performance, the F1 score is better when you train the model using your data. So the best thing is just train a model with your data, and you are going to obtain better results. So you can, if you don't want to do the training, it performs really well. But the best thing is just train the model with your data. And we don't work on also with only with the deep learning. We work with some other methods. We use morphograph to do segmentation. In this case, I showed the segmentation, the cell segmentation of 3D Arabidopsis and neuron segmentation. So there are several tools that you can use to do the segmentation. As I say, automatic process is really well, but sometimes it's really difficult to develop an automatic algorithm. In some cases, you need to generate the manual annotation. We generate this tool to track the cell image in 3D data. And once that we have this data, we are going to generate a lot of data. We are then, if we have enough data, we are going to train a deep learning model to solve this problem. But right now we are working on just generating the manual annotation. So I think that's all. Just as summary, I would like to say that deep learning algorithms has gained popularity due to high performance in several tasks. So as I say, deep learning is doing really well on reproducing these manual annotations. So you should take a look to do that. It doesn't require an expertise to train the model. As I say, you have the tools, and you don't need to do any programming. You just give where is the input, what is the target, and that's all. You don't need to worry about optimization and all those things. So it attempts to reproduce results similar to those obtained by a human expert. It's very well at doing that. So you should take a look. So as take-home message, if you find yourself dealing with repetitive tasks like segmentation, tracking, or classification, just try to use deep learning. Try to use deep learning to avoid this manual annotation. Finally, I would like to say thanks to all the collaborators. I don't know, probably I am missing some of my collaborators, but we have many collaborators, many of the Institute of Biotechnology, the Hans Zuckerberg, because it is taking care of me, the Hans Zuckerberg Initiative, and CONACYT, the GAPA, Institute of Biotechnology, and the Mexican National Laboratory for Advanced Microscopy. And I think that's all. I was almost done.
Thank you so much, Paul. That was great. Of course, we have a couple minutes, or we're just about at time, but maybe time for one question if someone wants to put it in the chat really quick or ask. Oh, okay. I see one from Michael. Any options on the use of models to generate ground truth? For example, one of the recent extensions for QPath allows the use of SAM to generate annotations that can be used to train cell pose models. Any links to something in the forum?
Yes, I didn't talk about annotation, but there are several tools. Fiji has Annotator J. This is really good for annotations. As you say, QPath has also annotation tools that you can use. And there are many annotation tools. I didn't want to go on that because I think that this is a lot of material, but I had given some workshops, and I spent probably 1 hour, 1.5 hours just talking about annotation tools. And there are several. Something that I really like about annotation is I don't remember, Annotator J. I use it. UPath also has good annotation tools. This is, I don't remember the name, but there is also another annotation tool that is really good. That you don't need to do the annotation, the manual annotation. It uses artificial intelligence to guide the annotation, and it helps a lot to. I don't remember the name. I don't remember, but there are very good annotations.
Well, I realize we're at time, but thank you for the question, Mike. Thank you, Paul, for the fantastic presentation and for joining us. It's been great to have you as our speaker. And I guess if anyone has a last burning question that they want to pop in the chat, please do so. But if not, thank you so much for joining us, and we really hope to see you at the next one.
Thank you. Bye-bye.